Let's first talk about lithium. Now, many different people are interested in lithium for different reasons. Today, I'll be focusing on only one, which is lithium is the heaviest element produced in Big Bang nucleosynthesis. And what that means is you can measure lithium and it leads you to the cosmological lithium problems, notice the S. So this graph is a nice illustration of what this is. And basically, there's two isotopes of lithium. There's lithium-7 and there's lithium-6. So we're going to talk about lithium-7 first. Now, lithium-7 was produced in the Big Bang. So that means that you can measure its abundance from observations of the cosmic microwave background with things like the Planck satellite. And the measurement that you get is this straight line up here, which is about 2.7 dex. However, you can also measure lithium-7 in the very oldest metapore stars in the halo of our galaxy. And we get quite basically the same measurement across a wide range of metallicities. So for the longest time, we thought that this was actually also the primordial lithium abundance. Now, the problem is these two measurements don't match. And because the y-axis is a logarithmic scale, that means that there is actually a factor of 3 difference between these two measurements, which is large. And that is the cosmological lithium problem. Now, if we look at lithium-6, lithium-6 isn't really produced in the Big Bang, but we can have lithium-6 being produced through cosmic galactic ray spallation, and that basically increases the lithium abundance as time goes on, so as metallicity increases. And that is what you see with these lines in the background here. However, we can measure lithium-6 in the very same stars that I was previously talking about, and we get some upper limits, but also some detections. And unfortunately, these detections are actually above those predictions. And so this is the second cosmological lithium problem. Okay, so if there's problems, what are the possible solutions? Well, first off, one possible solution, observational accuracies. Maybe all of these dots are in the wrong spot. Second off, maybe the lithium abundance changes during stellar evolution. So the key problem with this solution is that lithium-6 and 7 are the same element. So you expect them to have similar nuclear physical properties. So it doesn't make too much sense for lithium-7 to decrease whilst lithium-6 increases. To make a really bad analogy, imagine if lithium-7 was your water and lithium-6 was your coffee. No, the other way around. Imagine if lithium-7 was your coffee and lithium-6 was your water. You make some coffee and then you drink it. You expect to get an empty cup at the end, right? But what we actually observe is as you drink your coffee, you're ending up with more water but less coffee beans. So as you drink it, it gets diluted, which doesn't make any sense at all. So if this possible solution doesn't make sense, we have to resort to more exotic scenarios. Things like modified nuclear reaction rates, gravitational wells, dark matter, variations in fundamental constants. I don't know anything about these, so I'm not going to talk about it. Today's talk is focused upon the second cosmological lithium problem from an observational perspective. So let's talk about what we're actually observing. This is, there's 3 lithium lines. This is the only one anybody cares about. It's the 670.8 nanometer line. And what I've got here is both lithium lines, one at 0%, so the one in blue, and one at 5%. When I say percent, I mean lithium-6 to lithium-7 ratio. In the black is where the lithium-7 components are, and then in the red is where the lithium-6 components are. I want to stress that when we say we've detected lithium-6, 5% is some of the highest detections that we have. So this is actually one of the biggest differences that you will see. And the difference is, unfortunately, about 10 to the negative 3. So it's a really small difference. So what, in essence, we are doing is we're measuring the line shape. Okay, so what things affect the line shape? First off, the lithium abundance. If you increase the abundance, the line gets stronger. The isotopic ratio. If you increase the ratio but keep the abundance fixed, then the lithium-7 components will decrease and the lithium-6 components will increase. Rotation of the star. When the star rotates, the line broadens. And then there's also, of course, Doppler shift. So as the star moves backwards and forwards, redshift, blue shift. Now, unfortunately, all of these effects are partially degenerate, so it's actually really hard to measure. Okay, so if we have measurements, well, we're using the ESPRESSO spectrum, and it was picked because ESPRESSO gives us beautiful spectra. Now, the resolution of ESPRESSO is above 140K, which is massive, and it is some of the best. This is the best resolution that we have for these stars. Our signal-noise ratio is also the best for our targets observed to date, and it is above 1,000 for 2 of our targets. And we have 3 targets. So HD A4937 is that one star that has multiple lithium-6 detections in the literature. And then there's HD 140283, which is a null sample. Nobody's ever measured lithium-6 in the star ever. And then LPA 1543 is the most metal-poor detection of lithium-6 in the literature. And here I'm showing some of the beautiful ESPRESSO spectra. And I have actually plotted the error bars, but you can barely see them because our data is so good. So when now we have spectra, we need to get somehow the abundances out of the spectra. So to do that, we need to make models. So I'm going to first talk about the model atmospheres. Now, our model atmospheres are also called box in a star models because we only model the surface atmosphere. We don't care about the core because we can't see photons from the core. And so essentially, our models basically is what's contained within this ESPRESSO cup shot. Now, there's 2 different flavors of model atmospheres. There's 1D ones, and then there's 3D ones. Now, obviously, 3D ones are more realistic, but also more computationally expensive. So model atmospheres also doesn't directly translate into a spectra. So to actually get the spectra from this model atmosphere, we need to have the model atmosphere and then solve the equation of radiative transfer. Now, the only thing you need to know is that when we solve it, we can make an assumption called local thermodynamic equilibrium, LT for short. And this simplifies the calculation. So in the past, about 20 to 30 years ago, we were able to do 1D model atmospheres under LT radiative transfer. Today, we are able to do 3D model atmospheres, and we can drop the LT, so non-LT radiative transfer. Now, that was 30 years of computational advancement, and you might be wondering, is it worth it? And the answer is yes, because what I've plotted here is lithium for the same abundance under 2 different simulation conditions, one for 3D non-LT and then one for 1D LT. And you can see that there is a clear difference in the line shape. And just as a reminder, when we measure lithium-6, we are measuring the line shape. So this is actually quite big of a difference. And in particular, it's actually the 3D convective asymmetries, which is actually mimicking the effects of lithium-6. So how are our fits looking? Well, here I plotted the lithium line for our 3 stars. And in the black is the observed, the black dots. And there are error bars in the top panel. You just can't see them. They're a bit obvious. They're a bit more obvious in the bottom panel. And then we've also got our fits. And you can see that our blue fits are really good for our spectra. And for the residuals, the orange shaded region, that tiny bit, is actually our 99% confidence interval. So we have amazing spectra and amazing fits. Okay, so let's talk about our results. Well, looking at lithium-7, we haven't really touched the lithium-7 abundances. So the cosmological lithium problem, which is lithium-7, is not an observational effect. Lithium-6, however, we have actually revised our upper limits down by quite a lot. So we think, given these observations, there is no second cosmological lithium problem. Lithium-6 was most likely just an observational effect. In addition, our work got picked up recently by Fields and Olive 2022, and they actually published new galactic cosmic ray models and revised some of the lines in the background, which is in red now. And you can see that it roughly matches with previous, and also these lines are above our upper limits, which is really good because that means that both lithium-6 and lithium-7 can be depleted. So in summary, we revisit the long-standing second cosmological lithium problem. We find that there is no convincing evidence of lithium-6 in their metal-poor stars, and therefore there is no second cosmological lithium problem. And with new galactic cosmic ray modeling, there is now strong evidence for depletion of both lithium-6 and lithium-7 through stellar physics. And therefore, the likely solution to the cosmological lithium problem is actually stellar physics. And I'm going to end with, ESPRESSO can't solve all of your problems, but it's worth a shot. Thank you.